I guess we start talking. So, all right, just trying to get the audio balanced out here. I'm getting used to the noise in the background. Oh, I'm interpreting. Thanks. All right, trying to get into the right mood here. So, for what it's worth, I did have slides. Being in a business where we don't thumb drive very much, I didn't bring a copy, and the email got lost. So, you're going to imagine the most beautiful slides. They're not that fancy. We're up there. But unfortunately, a couple of my jokes are on there. So you're just going to have to imagine the funny jokes are on the slides, too, and just pretend they're there and laugh at appropriate moments. That's about it. It's that, and it's a way for me to make sure I get my actual talking points pre-approved properly. Because my name is Bill Layton, and my job is I'm the technical director for the Cryptographic Solutions Office at NSA. So that means commercial solutions are classified, all those certified high-grade products, all that kind of stuff. That goes through where I live. That nightmare? No. Wonderful certification process? No. The security is hard, right? All the standards and the complexity of actually implementing secure solutions, that's kind of the realm I and a few of my colleagues work in. And one of the big issues that we hit these days is what about quantum computers and what they do for us, what they do to us, maybe in the security business. And so that's kind of the theme of what I want to talk about today. So the plan of this time, assuming I don't scare you all off, is I'm going to geek out for a few minutes because you have to talk about quantum for a bit just for fun and because people think it's cool. And then I'm going to tell you why you don't care or why you don't professionally care. I mean, we're technical people. We all think that's cool. And then I'm going to go on and talk about some of the actual problems and the reality and sort of where we're going and why this is easy, why this is hard, kind of the state that we're facing. So that is the overall plan of what's going on. At a high level, let me say, my goal in life is to change quantum from a scary security word to a cool technical word that has nothing to do with security. So that's where we're trying to go. Like, for the moment, though, quantum is scary. You should be slightly scared if you're in the cybersecurity business. Let me say a bit about why. So, geek out time. What is the story on quantum and quantum computing? Well, this may come up a couple of times. Arthur C. Clarke, 2001: Space Odyssey author. If you go poke around, there are a few famous things he said, many famous things. Clarke's laws. One of them is any sufficiently advanced technology is indistinguishable from magic. There's also one that says any sufficiently arcane magic is indistinguishable from being technology. When it comes to quantum mechanics, I think I'm kind of in the magic camp. It's really wild, and why it does what it does, frankly, nobody, I would argue, understands. This is not advanced technology. This is just weird. But that doesn't mean we don't have good rules for how it actually works, and we can leverage it somehow. So observations got made years and years ago, right? People were thinking about what happens when things get very small. And by small, well, you can go back to Greek days, right? It's like, okay, I'm going to take my bar of iron, I'm going to cut in smaller pieces, and you can theorize about atoms and have small little bits of stuff. But when you got to quantum mechanics, we got into questions about what happens when, like, the fundamentals of nature get small. Is space small, right? Do we live on graph paper where everything lives on dots, or do we live in something where you can keep getting smaller and smaller and just keep going forever? And the answer to that or question kind of was yes, or maybe neither. When science got down to these really teeny things, life got strange. And what happens is things just get fuzzy. They don't get smaller, they just get blurry and mushy. And the strange phenomena you get is, came up with the word quanta. Yeah, things are fuzzy when you're not looking at them, and then they resolve into specific values when you look at them. So the general rule of quantum mechanics is you have things, when you aren't looking at them, they're blurry and hopping around and doing strange magic. And then when you look, suddenly they behave nicely and they're nice little particles and things line up neatly. The simplest example you can run into every day, I think, is sunglasses, actually. If you have those fancy polarized sunglasses, then the way they work is light coming out, when it's coming into the lenses, you can view light as going up and down or horizontal. So vertical, horizontal light coming in. And your sunglasses basically block all the horizontal light and they let the vertical light through, because it turns out when light glints off the surface of a car hood or a window, it changes polarity into this horizontal. So it's a glare reduction. It's a cool feature. More practically, there are these nifty little crystals you can get where if the light's polarized vertically, it goes one way. If it's polarized horizontally, it goes the other way. Cool. What happens if it's polarized diagonally? That's valid, or maybe not. This is where the weirdness started. So the simple answer is, if you have diagonal light going into one of these things, it doesn't go in between, say, right and left. It makes a decision. It hits your crystal, if you will, and it's going to decide, am I vertical today or am I horizontal today? And it will make a choice and become vertical or horizontal and bend in the appropriate direction. You will get two different beams coming out. And how does it decide? Well, Einstein was upset with this roll dice with the universe thing. God does not roll dice with the universe, famous quote. For all practical purposes, God rolls dice with the universe here. We don't know, right? It's this little bit of light floating along, and it hits, and it goes, well, I'm 30% vertical and 70% horizontal. Let me go get my probability thing. I'm going to be horizontal now. And it becomes that. And that's just weird. But that's the first step of the weirdness. So the quantum mechanics can get really big. We're going to reduce this a lot. I'm a mathematician by training. I did cryptography. I'm now in implementations. But I like the mathematical neat definition. So the simplest thing you can do with quantum mechanics is like the light. You have this thing called a qubit. It's going to have two states. It can be up and down and horizontal, vertical, horizontal. It can be the electrons here, the electrons there. It can be the stuff spinning one way, spinning the other way. Whatever your physicist wants to do for his quantum thing, the simplest thing you can have is two choices. And we're just going to call them 1 and 0, just like a bit. And, hey, I can store values. I can have a 1, I can have a 0, and whatever this machine is. Cool. Except when I do this in quantum space, I can also have something that's part 1 and part 0. What does that even mean? Well, it means it's part 1 and part 0. I don't know. It's the rules of quantum mechanics. But when I go and read it off, I get a 1 or a 0. And somewhere behind the scenes, the universe rolls a dice and goes, okay, great. It's going to be a 1 today or a 0 today with some probability. The qubit, okay, weird. Now, that's the first weird part. The second weird part where stuff gets totally crazy is what happens when we have two qubits. So I have a bit that can be a 1, 0. I have a bit that can be a 1, 0. How do I describe this thing? And well, there are 4 possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. Great. Cool. But if I want to describe this thing, the weird part is it's not how much 1, 0 is the first bit and how much 1, 0 is the second bit. What happens is each of those 4 combinations is a state I have to deal with. There are 4 different possible probabilities I have to keep track of. Okay, not too bad. 4 states, 4 probabilities maybe. Oh, and then the really dark magic happens. So you can set one of these things up so that it's, say, in the 50% of the 1, 1 state and 50% the 0, 0 state. So I have my little bit of light here, and it's half 1, half 0. And I have a little bit of light there that's half 1, half 0. But it's not really that. The two things as a system are 1, 1 or 0, 0. And now I can take those bits of light, take them very far away from each other, and then I look at one of them, and it decides, am I a 1 or a 0? And the wacky thing is, the other one, well, the whole system is either 1, 1 or 1, 0. So once the first one decides it's a 1, the second one's a 1, 2. If the first one decides it's a 0, the second one decides it's a 0, 2. And it doesn't matter how far apart they are. And that's where people got really, really worried, because I now have these two things that somehow or other decided on their value in different places in the universe, and yet were connected. And then, like as I said, magic and confusion reigns, and people get upset. And then people try to figure out, well, no, maybe they decided what they were before you pulled them apart. No, it turns out you can do experiments. They don't do that. Maybe no, it's just the way life is. Yeah, it doesn't work with relativity and the speed of light. Maybe it doesn't. If you're a physicist, you can spend all your time hammering this out. Whatever. It's just reality. So now, extend that out a few more notches. And I like saying, suppose you have 32 of these. 32 of these little bits. That's 4 billion states I have to track. 4 billion probabilities. That's a lot. And this is where quantum computing came from originally, was realizing I got 32 particles. I need a 4 billion state computer classically to track this thing. Oh, I have a 64-bit thing. Now I'm up to, oh no, I'm in trouble. 120-bit? No, it's like quantum systems fundamentally do not model well in classical computers. And so the notion was, well, the universe seems to have no trouble computing with this stuff. I mean, it's doing it all the time. Maybe I can use that quantum thing to do some computation on my quantum problem. And quantum computing was born. So, seems like a decent enough notion. I have these qubit things, and I'm going to use them to actually compute quantum stuff. So, how do you actually do this? Oh, now life gets trickier. So, unfortunately, one of the few pictures I haven't thought I could show you, right? If you ever see a picture of a quote-unquote quantum computer, what you're going to see is this cool gold thing hanging down from some platform or frame with wires dangling on it and some racks of equipment behind it. What is it, really? Well, the quantum thing, the bit that's super cold and super teeny and managing the bit of the universe is sitting at the bottom of that. It's probably a little teeny part. And what is it? It's some chip probably that's keeping electrons in bin A or bin B or spinning them a certain way, or it's a superconductor with a current going one way versus the other. Whatever the experimental physicist wants to do. You don't even see that. And then this cool gold thing that you see, that's the refrigerator. That's not the computer. That's the refrigerator that cools the thing down. It's a cool refrigerator. No pun intended, right? These things are amazing. Look up dilution refrigerator. It's an amazing piece of technology. You put the liquid helium in, and then it uses something this isotope split in liquid helium to get even colder than normal liquid helium at the bottom. These things, 50 years ago, you'd be, anyone got that cold. Now you can just buy the things and make them. Cool. In the back, there's a classical computer. Because what's really going on when people say I built a quantum computer is that you've got these little quantum things and you're trying to push them around. So I'm trying to push this from 1 to 0, maybe by hitting it with a radio signal or some light or changing a magnet around it or something. It takes a regular computer a computation to do something with that. So it's true. I can take like a couple of these quantum things and I can treat them as bits and I can add them together. Actually, I'm cheating already. It turns out you can only do reversible computations, so you have to have some ancillary stuff. Dodge that. So you can make this computer compute like you're used to. But every operation this computer does has a whole class of computer behind it that's chugging away to make each step happen. So people have come up with some really crazy stories about quantum computers. Next generation, you have a quantum computer laptop. Why? Because it turns out that a quantum computer can theoretically compute anything a normal computer can do, but badly. It's like thousands of times slower. It's horrible. Because every operation of this quantum computer requires like a standard computer behind it, like driving it. So it's inherently slow. So why do you want this? Well, you want this because it turns out that there are a couple of things you can do on a quantum computer that classical computers can't handle. So if you go back to that 32-bit thing with 4 billion states, weirdness happens in here. There are 4 billion states, 4 billion values in this machine chugging away. But what people tend to forget is when you read out of this machine, you get a 32-bit answer. And that's it. There's no magic 4 billion states anymore. You get a 32-bit answer. So you can do certain things faster on a quantum computer, but only very certain things. And that's it. For most computations, it is not exciting. For some things, however, it can be. All right. Make sure I don't forget something here. Okay. So let me frame one more thing just for context. The word quantum computer gets overloaded in a couple of places. So you can go now on various cloud providers and get access to a quantum computer, in quotes. And quotes may not even be the right phrase. It is a quantum computer in some sense. It's a machine that uses quantum states to do things. But it's not something that I professionally find really interesting because there's sort of two different quantum computers people talk about. The quantum computer I was just talking about really is sort of a theoretical object. I'm a mathematician in principle here, right? There's a theory. It says I have ones and zeros. I do stuff. The quantum computers built today are physical machines. Well, when I put that particle in, and it's a 1 or a 0, or a bit of a 1 or a 0, that's a very touchy object. It's almost like an analog computer from back in the day. If you don't open your history book and read about analog computers, right? You solve your differential equation by getting some capacitors and resistors and inductors and wire them together in a circuit that looks like your differential equation, and then feed in a signal, and you can kind of solve some problems that way, but the parts are never perfect and noise gets in. The quantum computers we have today are kind of analog-y, right? You kind of feed in the values and you very delicately touch them, and air kind of creeps in and things start wandering, and you kind of hope you do your computation fast enough that the result is pretty close to what you want at the end. And then then you do it again, and maybe you do it again, but you can do a really short calculation and have a decent chance of getting the answer you want. But there's noise in this thing. So one of the rules of quantum mechanics is, going back, when you measure something, it loses its quantum magic. Measure is not a human being necessarily measuring. It could be a cosmic ray hit the thing. It could be an atomic particle decayed nearby. It could be the truck drove by and shook the machine. These things are very delicate. So, yes, there are quantum computers today. They're often called NISQs, Noisy Intermediate Scale Computers. They're more than a gate, maybe. Some have thousands, but they have noise. You can do experiments on them. You can work on them. So why does this matter? Well, there's a cool idea that came out a few decades now, whatever, called error correction, which is kind of like error correction that people are used to in normal digital stuff. Right? So normally you do comms, you send like some extra bits, you have this cool checksum, and you find your friendly coding theorist who tells you, and then if this is a 1, 2, this is a 1, 0, 0, that means that the 7th bit had an error, so go change that, and now you've got your signal back. Anyone who works in data comms, you do this all the time? Yeah, it's like that, but not in quantum. So if I build a quantum system and I want to actually make the thing reliable, well, I've got a couple options. One is I just make the thing better. So I go for isotopically pure silicon in an even colder environment with more radiation shielding around the outside and more precision. I can do some of that. The other thing I can do is I can say, I'm going to put redundancy in. I'm going to put in 3 qubits physically for every qubit I want. I can put in 3,000 qubits physically. I don't know how many I need, right? But so I say, I'll put in redundancy in my calculation, and I'm going to do computation. And the magic trick here is that when I read data out of the quantum computer, I don't actually have to read all the data out. So if you're really clever about this, what you can do is you can set your computer up, do some work, and then what you can read out is just the error. You don't actually read the value, the super delicate value. You just do a little read on the side and say, so is there an error in there? And if there's an error, the error is in bit 7. I'll just go over. I don't know what bit 7 is, but I'm going to change bit 7. Okay, compute again. I'm going to do another error check. There's an error in bit 9. I'm just going to go over and flip bit 9 back. Okay, quantum error correction. Black magic, white magic, I don't know. Magic of some sort. But, okay, it's a concept. Does it work? Well, on paper it works. If you look at the research right now, the state we're in is, I think it was last year now, a paper came out of an example where they put a bunch of quantum gates together, did error correction, and they achieved performance that was the same as having one normal bit, one normal qubit. It had the same error rate they would have had if they just started with just one bit in the first place and just used it, which sounds kind of bad. Actually, it's amazing work. So if you think about it, if I have like 100 bits, there are 100 bits that have the potential of having errors in them now. So the bigger I make this thing, the more errors are going to happen. And the more computation I do to correct for errors, the more errors are going to happen because I did computation and measured things. So the error correction itself creates errors. They've gotten to the point where the error correction is correcting as many errors as the error correction creates. This is a little like if you're doing fusion, and the people say, I achieved fusion break-even, right? I finally get to the stage my fusion reactor makes as much energy as it takes to run the reactor. That's not going to build your power plant, but still amazing. It's an amazing step forward. So that's where we are. Quantum computers, it's going to be the achievement of the 21st century in physics if we manage to get the error correction to the point these things can run for lengthy periods of time. But there's nothing's stopping us other than some really brilliant engineering as far as you know. So one last Arthur C. Clarke quote, right? He said that if a very old distinguished scientist tells you something is possible, they're probably right. And if a very old distinguished scientist tells you something's impossible, they're probably wrong. So, yeah, quantum computing. Is someone going to build one of these things? Maybe. When are they going to build it? Don't know. Not going to be tomorrow. But when I say, what are these things? What I'm worried about in the security space is what we call a CRQC, cryptographically relevant quantum computer. So the first actual useful fact, now that I'm 20 minutes in, I will stop geeking out and talk practically, is if you actually can build one of these computers big enough to actually do cryptographic calculations. So it can't be 32 bits, but if you look at elliptic curve cryptography, you need 700-bit calculations to do thousands. So if you get into like thousand something, right? But basically, if you can build one of these things with enough logical, consistent data to do the math required to do cryptography, then effectively, there's a little engineering overhead here. You've built a computer big enough to attack elliptic curve cryptography, finite field cryptography, RSA, all the public key cryptography we've used for the past 40 years, 50 years, you can attack. And when I say attack, this is not, I can attack it a bit. The attacks run almost as fast as the encryption. There's an order of magnitude, but it's within spin distance, whatever. Basically, if someone, in booth, whatever down there, showed up and they actually had their laptop quantum computer, this would be crypto Armageddon. This is like, go unplug all your network comms, because every bit of patch management you've got, every signed authentication, every website you go to, it's all gone. You can't trust anything. Just so much is built on this, on those algorithms, that the day someone has a machine this big, the only way to secure yourself is to disconnect from everything and hand inspect everything that comes in or something. It's just one of my favorite World War II stories is actually about what happened when they had a near security breach post D-Day going through northern France. Eventually, they found out that the stuff, the gear there was a truck stolen by a farmer. It's a whole saga. But there were a few days there where all the radio comms went down, and they went to put people on motorcycles with written orders running around to relay messages because they weren't sure. That's the world we would live in if someone popped up tomorrow with a quantum computer that was this big. And that's why this is a challenge. It's a huge physics challenge. As I said, people are not solving this tomorrow. But when it gets solved, we have a really big problem. So, I sometimes say there's only one thing that you really need to take away from this, maybe two. So the thing you maybe need to take away from this is, if someone gets a quantum computer, really bad things happen to a lot of cryptography. Actually, the one thing you need to know professionally, since, we're talking, military comms, government, whatever. Well, National Security Memo 8, National Security Memo 10, White House policy. In a nutshell, quantum computing is a big threat to cryptography. It is the national policy that we are going to do something about this. And if you go look, there are timelines that say we are going to do something about this. So, people often come up like, how bad a threat is it? When's it going to happen? What's the chance? Is someone building a quantum computer? I'm like, look, no one's going to have one tomorrow. Like I said, the physics, it's a ways to go. That being said, we can't fix things tomorrow. This is a massive change in the whole underpinning of how we do cryptography in every place. So, when you look, there is an order from the president that says, policy, we're going to fix this. It has details. So the details are, go figure out it's kind of what you expect. Go find the problem. Go fix the problem. Do it in like a decade, which decade seems relaxed. A decade is not relaxed. We're on government timelines. We've been through some times we've changed crypto in DoD systems before. It took a decade to get most stuff sort of fixed. Think about how long it takes to get the Windows XP eradication order. I love that one. The years of get rid of it. No, come on, no. How? All right, if you still have XP, you have to go further up in the department to get a waiver. Further up. Why do you still have it? We've got a decade to do a very large shift. So, 20 minutes of what's quantum, why you care. It's cool stuff. That being said, doesn't matter whether you think it's cool, doesn't matter what you think. The orders are, fix the problem. Fix the problem. How do we fix it? Well, one of the worst things I run into in this space is people who think that the way you fix the quantum threat, if you will, the quantum computing threat to cryptography, is by using quantum. So, yeah, if someone came along and said, oh, look, our enemy has hypersonic missiles, how do I solve that? Well, I mean, I guess I want hypersonic missiles too, but I don't defend against it by building a hypersonic defense thing, maybe. If someone says, I build a better explosive shell, I don't build, well, maybe I build more reactive armor, but mostly it's like I want thicker armor or armor that's different. You don't defend against quantum using quantum inherently. This word quantum gets used in lots of different forums. So you're going to run into various applications of quantum. So one of the things you run into is people who say, I need to use quantum to be the source of my randomness in things. Quantum random number generators. That's a really interesting one, because the universe, as I said 20 minutes ago, right, the universe plays dice. The universe generates random stuff when it does quantum mechanics. You can use that to make random numbers. It's cool. It's also not the only way you can make random numbers. So, yeah, you can make random numbers by looking at thermal noise of diodes. You can look at it famously by taking a camera and filming lava lamps. I mean, yeah, if 30, 40 years ago, if I had to make a random number generator, I would find that an engineering challenge, because systems had to go and sample a random source and use that for ones and zeros. We're in the 2020s. In the 2020s, we have things called entropy pools. Basically, you take whatever random stuff you can get, you throw it in a big pool, you compute, because computation's way cheaper now than it was in the 90s, and you just do a bunch of math, and you get random. So there's nothing inherently magic about quantum random that makes it a great solution. There's also nothing that makes it a bad solution. So let me be clear, right? Quantum random number generators can be perfectly fine random sources. It's just you don't need a quantum random source to be protected against quantum computers. The two are disconnected other than they have the word quantum in them. So let me just make that one clear. The second one you run into is quantum cryptography. So that other trick I talked about, where I take my bits of light and I separate them, and I look and I get random stuff at both ends. If you're really clever about how you do that trick, and you do vertical, horizontal, or maybe diagonal one way and diagonal the other way, and some extra commas around the outside, you can actually use that to get a shared secret between two endpoints. That sort of mixes random and another feature. You can detect if someone's tapping your line. Okay, issues here. First off, tapping your line is not actually someone tapping your line. Tapping your line is someone vibrating the line, something emitting the line. It's a very touchy process, but you can do it. It is one of the coolest lab experiments I've seen, right? You can do quantum mechanics and see the secrecy flying around. It's really cool. I don't know of anybody in the security business that thinks this is a viable solution anytime in the near medium-term future. NSA has a statement on this. The UK has a statement on this. Lots of industry believe has statements on this. You can use this as a security mechanism. As a practical solution, you have to build things with very precise lasers and sensors. You have to have special comms channels. You have to completely rebuild your comms network. And all this gets you is some shared secrecy. You also have to deal with denial of service issues. You have to deal with authentication issues. You have to integrate it into other infrastructures. It's just switching over and just doing this quantum thing to provide security. Yeah, there's a challenge there. There's a whole essay there. I'm not going to go into it, but I just want to say, quantum cryptography, the official NSA position you're looking is we're not using it in national security space. And I think just generally, if you look in the security community in general, no, it's not something someone expects to use. If you're in physics, it's cool. And I've got to say, when we get to quantum computers and you want to exchange quantum information from one computer to another, or if you're in the quantum sensing business, you have to have this, the phrase is entanglement. You have to link your sensors up. This pretty much the same technology you need to do the quantum cryptography, and that the companies are developing there, that migrates over into being able to exchange quantum information. I don't want to get to try to define that between systems. So cool technology. There's lots of stuff that's going to get used for the future, just not in the security space, not where I'm working. So pushing it out of the way, how do you deal with this problem? Well, all right, maybe I'm biased, but no, I'll claim I'm right. I'm a mathematician by training. The way you solve the quantum computing threat for cryptography is with math. Yeah, math. Scary word. But math. It's cool. Math. No. So rolling back a bit, right? Quantum computers, as I said, they're really bad computers. They're horrible computers, except at very specific operations. Well, the unfortunate thing is that operation they're good at is really good at solving the period finding problem, the factoring discrete logic, the algorithms everyone's used to for public key cryptography. Turns out that's that's like the one mathematical problem they're good at. This is where I ponder fate. The universe playing a great joke on cryptography. How did we end up here? Well, there's some rationality here, right? Those algorithms were chosen because they had some nice properties. They were easy to compute with. They use periodicity, the fact that things repeat regularly. It turns out the quantum mechanics, kind of do quantum mechanics, you have to do Fourier transforms. Periodicity is kind of built into it, so there's sort of some similarities. You can kind of expect maybe there's something there. I don't know. But, back in the days when cryptography was starting up as a global thing, and people are inventing RSA and DSA and ECDSA and all those things, every mathematician worth their salt published a paper saying, hey, I've been researching this, and you can use it for cryptography. Give me a grant. Okay. Well, some of them were right. I mean, actually, there were a lot of ideas for cryptography out there. Some of them were wrong, by the way. Some of those things turned out to be horrible ideas. They were totally insecure, but some of them were right. Why didn't we use them? Well, we already had some ideas, and also some of them were pathetically complicated or whatever. I mean, there's one where it's like your public key sizes were a megabyte, which, especially say in the 90s, like that's a non-starter. But I mean, on paper it works. Well, so when this became a bigger concern a decade or so back, everyone went back and dusted off all those papers, did more work, and NIST fired off we always like to call it the not a competition, right? NIST has run competitions. This was explicitly not a competition. It was a standardization process with a lot of entries, some of which would be selected. Not a competition. There's some meaning behind that phrase. And they just about finished a couple of years ago. By just about finished, what I mean is they picked at least the first round of the mathematics you need to do cryptography that quantum computers, as best anyone has a clue, don't impact. Yay. Now, when I say just about finished, what that means is we've got the math formulas and the general guidance of what to do. What is going on right now as we speak is the finalization, right? There are draft specifications out there, the final actual spec saying, here's how to do your cryptography so a quantum computer doesn't affect you. That's what they're working on now and will be coming out one of these days, right? It's supposed to be this year kind of thing, right? There will be an actual specification that says, do this cryptography, and quantum computers are not your problem anymore. So, joke that you're not seeing if I had a slide up. What does this mean? So, once NIST is done, what do we all have to do? Well, the first thing is we need to take all of our AES 256, because that's what everyone should be doing, right? NSA told everyone to do 256. The rest of the government's 128 to 256. And replace it with, hold on, AES 256. Yes, okay. So, like when I said the quantum computer is good at certain things, it's not very good at symmetric cryptography. It has some impact, but it turns out going to AES 256 from like the 192 was really easy, and everyone did it anyway. So that's all you had to do to protect yourself, and we did that 10 years ago. So the whole swath of cryptography, symmetric key stuff, hash functions, if you're into that sort of thing. Where as long as you use the sort of bigger sizes that like at least NSA has been putting out as guidance for national security systems for years, you're good. Yay, problem solved. Now, if you're going to work in the realm of public key, though, what you do is you take all of your key agreement stuff, so the elliptic curve Diffie-Hellman, the classical Diffie-Hellman, the RSA encryption, and you replace it with what I am sad to say is called ML-Chem. I'm sad to say it because it was originally by the proposers called Crystal Kyber, and if you're a sci-fi Star Wars geek, that sounds way cooler than ML-Chem. But fine, you replace it with ML-Chem. And if your national security systems use the biggest size because we're paranoid national security systems, whatever. But if you've never seen it, you should look at a thing called CNSA 2.0. It's NSA's guidance on this, by the way, which is I'm citing. So ML-Chem, new cryptographic key agreement. It is to the first order, and I'm going to say second order in a minute, but the first cut, you can just drop it in as a replacement for the key agreements you had in the past. The message flow is the same. You make a key, you send a message, it gets decrypted at the other end. Okay, yeah, there's fancy math based on pool lattices and structural modular things. Yeah, fine. Who cares, right? Unless you're in, geek out in the crypto math, it is a black box thing. You take the thing called elliptic curve Diffie-Hellman out, or you take the thing called Diffie-Hellman out, or you take the thing called RSA encryption out, and you drop in this thing called ML-Chem, and it looks the same, and you just go on with life. And that is it. What about signature? Well, signature, you take the RSA. Oh, wait a minute. RSA is good for both signing and encryption. Yeah, I'll say more about that in a minute, too. Or your ECDSA or your DSA. And you replace it with something called MLDSA. Again, I'm sorry. It was originally called crystals dilithium, which, if you're a Star Trek fan, sounds really cool. Yeah, there was a Star Trek Star Wars thing going on in submissions. But I don't work at NIST. NIST likes using nice names that say things like, structured, lattice-based digital signature algorithm for their title. Okay, it doesn't sound as cool as Kyber, but whatever. What do you do? So those are the names now. But again, it's a drop-in. You just take this, you take all those signature things you did in the past, treat them as black boxes. You don't care how they work. No. Do you really care how they work? You don't care how they work, right? It's a cool crypto demo, but you don't care how they work. It's a signing thing. You rip out the old one, you drop the new one in, problem solved, everything else works the same, life is good. We got 10 years to deploy patches, we're great. Mostly. So now's where we have some fun. Nuances. I should say MLDSA is not the only thing in the CNSA suite. There's already an algorithm there called LMS. There are a couple other things. They're to be used for software signing, so I should point this out. It's a very old algorithm that there's already a standard for. It's good for signing firmware or signing software for distribution, and you don't have to wait till the year for NIST to stand up another FIPS thing. You can run it now. The standards exist. The ITF has them. NIST has a guidance document on what to do. If I was putting stuff out there in the field ahead of sign software, I'd be looking at this fast. It's really, really kind of good for that. That's its own little discussion as to why. I'm not going to bore you. General signing doesn't work well with it, but for certain applications, it's really cool. There are a couple other signature algorithms floating around. No, we're not going there at the moment. This is running another round to come up with new stuff. We will go there in a second. I'll say something. But what are we really facing? All right, so first order goal here. All everyone has to do is go find all their cryptography, find all the spots that are on the list of bad things, replace them with the new replacements, just drop them in, problem solved. Okay. So first order, they all work the same. Good. Well, next thing, they almost work the same. One of the early observations that came up, RSA was a cool cryptographic algorithm because RSA, you can do signing to authenticate things, like sign patches, sign email, and you can do encryption, like sending secret messages or encrypting email, with the same math. Literally, it's the same formula. You just sort of relabel the stuff. It's really cool. You can do that. When we went to the elliptic curve stuff and also some of the final failed things, whatever, you have to use different math to sign than you use to encrypt, but you use the same secret underneath. It's kind of the same underlying math structure, but you do just different formulas. And that started popping up in weird places. Like, if I'm issuing encryption certificates to someone, well, actually, no. This is what's interesting what's in government. This doesn't apply for doing escrow things and issuing encryption. But on some PKI settings, when people do encryption certificates, if someone generates their own key for encryption, they're supposed to prove that they have the key before a certificate's issued to them. They tend to do that by signing something with the key. But I'm signing something in an encryption certificate that's kind of weird, but it worked because the math kind of worked. NIST actually made an exception saying, you just want to prove you have the key, even though it's an encryption thing you can sign, but normally we won't want you to do that. Yeah, so people have built systems based on that for years. Well, in ML-Chem, MLDSA, the underlying math problem is the same, but the structures are different if you can't do that anymore. So people who built PKIs, there's an edge case where this particular business process doesn't work anymore. It was kind of a cheat, but it worked, and people used it for 30 years. Okay, that's minor. Probably doesn't affect too many people. All right, another one that we hit though. It's TLS. TLS is a fun one. So I'm going to try to be careful with my language here, right? So when the ARPANET was first founded, created, invented, whatever you want to call it, everything was in the clear. No one did cryptography, right? It was a few labs, you sent stuff, experimentation. When we got to the stage of I want to go buy my stuff on the internet, people don't like sending your credit card numbers in the clear, so we started encrypting things. Well, cool. But you don't encrypt everything, right? You have to know who you're talking to. There's some data that flows around. I want to know what the website is. I want to be able to see some traffic and manage things. So there's a spectrum of encryption and encryption goals on the internet. At the far end, and I'm not taking a position on what's right here, but the far end, think like Tor kind of thing, right? You set systems where maybe at most someone can tell that you're communicating. They don't know who you're communicating with, what you're sending, what's going on at all. And if I'm sitting here worried that my evil regime or hostile regime, whatever, I'm in a dictatorship or something, and I want to communicate securely, I might want that. But if I'm, say, sitting in a defense enterprise, I don't want everyone at their desktop doing their work to have communications from their computer to the entire world where I literally cannot tell that they even are communicating or who they're communicating to or what they're sending or what's coming back to them. What I tend to want is some sort of filtering where I go, you only talk to the things that are safe, that are within some national boundaries. I want to inspect to see when you're offloading a whole lot of files that they aren't the sensitive files you're not supposed to be sending. I want to see stuff coming in. Is there malware in there? So there's this range of options in terms of how much security and what's encrypted and what isn't, and what spots where you might want to decrypt or re-encrypt. And this is a very loaded topic. So I'm not advocating for any position. Depending on your mission space, you have to make different choices, and depending on your threat model. But a feature of TLS that comes from the fact you used RSA back in the beginning is if you have a TLS server and you take the private key of that RSA certificate off and say, slap it on a laptop. By the way, don't do this casually. This is bad. You're not supposed to take the private keys off and walk around with them. But if you did that and you clip into the comms channel, you can passively read all the communications and decrypt it all, just on the side. You can collect the data. You can come back later and decrypt it easily. And if you're a network admin trying to find what's going on, that's kind of cool. Some government regulations and finance industry spaces, not in the U.S., I believe so much, I'm not an expert on that, actually have sort of required implementations like this where you can monitor some of the comms going through systems to see if fraudulent stuff's happening and have tap points. Things were built around this architecture. But that's kind of unique to this RSA notion. Now, what's happened was as TLS advanced and went to TLS 1.3, it was built on a different structure where you don't have these fixed keys on the servers that do encryption, and you can't do that anymore. Now, okay, I have to acknowledge you can sort of in TLS 1.2 do it because ETSI disagreed with the IETF and wrote a standard for how to modify things to do that, but it's a loaded topic. Anyway, a consequence of this is that because the people writing the TLS standards really like this feature that you can't casually monitor stuff, they are essentially at the moment, live debate, but they seem to have a solid position, they're only going to put post-quantum cryptography in TLS 1.3 because it comes along with this passive monitoring is hard feature. Okay, so whatever the motivation is, suddenly what I told you is not go to all your systems and swap your RSA for MLChem. I just told you, by the way, swap your RSA for MLChem, but if you're doing TLS 1.2, you can't. So, schedule a TLS 1.3 upgrade, everybody. I don't know how that will turn out, but it seems likely that as a side effect of, political may not be the right word, but as a side effect of positioning in the standards bodies, TLS 1.3 is going to come along as a mandate with the quantum transition. Or maybe not, but likely. This is where the technical mess starts. So we have unintended consequences. The next problem we had as a technical thing is, they said you can just drop these things into black boxes, size. So the one other picture, unfortunately, I don't have to show you. You can go online and poke around for algorithm sizing tools. I just pulled one down for this. RSA, when we did RSA and Diffie-Hellman, we were talking, early days people did 1K, did 2K. If you look at the SA guidance for what you literally today, when you don't quite have the post-quantum ready, we're saying 3K kilobit sizes. When we went to elliptic curves, the math to elliptic curves is a little bit harder to chug through, but the numbers are smaller. You're talking 384 values, you need two of them, so about 700-bit values. Yeah, you can be nitpicky, and I'll use half. I'm not going there. Just think, you need about 1,000-ish bits to do cryptography the way we've done it for the past 20, 30 years. So, post-quantum, the standard we're putting out, the worst case, instead of 1,000 bits for your cryptography, think 7,000 bytes. So just casually, just factor up a size of 10, maybe, I don't know, maybe 5, 7, these things are big. So one of the reasons we didn't do this math years ago was the 5 megabyte public keys. We've come a long way. We're down to kilobytes. Nevertheless, these new algorithms we're using are bigger. And that may or may not be a major problem for everybody. So if I'm running TLS on a 5G cell phone and I say I have to send a few extra 1,000 bytes to set up my connection, nobody cares. Like the little graphics that are popping up on the side of my website are way bigger than this. Just nobody cares. It's easy. If on the other hand, I'm building a tactical battlefield system where I'm trying to squeeze every bit of data out I can, this could be a big problem. More practically speaking, even in the internet standards, this became an issue because what happened is the size pushed over the limit for a single network packet. So a lot of things with network flows actually start behaving a little oddly. And a lot oddly, right? So it's possible that some buffering can happen. People are tweaking buffering systems for that. If you're using IPsec, it turns out because of the way Ike v2, the standard works, you have to send your public key in the first packet, but the first packet is the spot where you can negotiate needing more than one packet. No one built the standard to allow you to say, hey, I'm going to need more than one packet to send my first packet in the first packet. So essentially what happened is for IPsec, the IETF actually had to say, fine, we're just going to set a quantum vulnerable thing, but we'll send it anyway, maybe. I guess you can send none. That sounds bad. It was just clear. And then I'm going to send something. By the way, I want to do a quantum thing too. Oh, okay. And then we get a whole lot more packets to the quantum resistant algorithm. And so some of that under the hood plumbing had to be changed. The good news is the standards are there. The RFCs are done or about done for all of this. Commercial implementation started to experiment, but it is different. And so is this going to break when we get into noisy, contested environments? How many applications is this bandwidth thing going to burn us on? I don't know. If I'm sitting at a nice desk with a web browser, nobody cares. This is the noise. If I'm building constrained things, very small channels, power-constrained devices, our little RF things, this might be a real problem. And frankly, right now we're at the stage we're trying to fix the 80% common internet use case and just beginning to learn what's happening in the fringes. So there are some issues, right? That's where we hit issues. So that's enough technology. The business side of this, where are we going to end up? So first problem that's going to come up is, money or time or resources. So I want to say nothing's free. Well, guess what? Some of this might be free. I fully expect my web browser will be quantum resistant the day after NIST drops things. Forget it. You can't get non-NIST compliant. If you're running a Chrome right now and going to Cloudflare, it's doing a non-NIST compliant post-quantum thing a good chunk of the time anyway, and you probably don't notice it. It's things that update, regular commercial stuff. All that's going to have to happen from the government standpoint is, look, the new standards, the new acquisition requirements are going to be include the quantum-resistant algorithms. And there's software updates. Woohoo! They get included as features in the next little while. The next things you acquire have them. The STIGs, the configuration guides should say, turn them on, people. Yeah, we want them on. You start running them. 10 years from now or so, we go, turn the old ones off. Then things break because we messed up. Okay. But hey, there we go. Problem fixed. Great. Some other things are going to break. Hardware. So it's my question, right? It's 2024. Do you know what mathematical algorithm is used to sign your device drivers? Right? All the products you have, what cryptography is in them. That is actually the big headache, right? We don't know which things we're going to have to replace because we can't update. The web browsers will be fixed, right? Operating systems, but how many odd appliances do you have? How many weird bits of equipment? How many odd applications that are in-house builds you have that have cryptography in them? Those have to be fixed. That's a bill. And what's it going to cost? What's the time? How are we going to get to all this? So I should leave time for questions. So let me leave a bit of hope, right? This is a spot where we know it's going to be a long road. Some things are going to be easy fixes. Some things are going to be slow. The biggest problem right now, if you go look at SM8 and SM10, what they say is, step one, the thing we're all supposed to be doing now is inventory all your stuff and start finding and scoping out the problem. Find the problem, figure out what's going to cost you, build the plan. That's where we're at. The solutions aren't out yet. NIST isn't done. The solutions are going to come out over the next year or two. But finding it. Now, the corny answer for how answering the questions you get from OMB and NSA, what things you have to fix, don't do this. You can write everything, right? Like almost everything we have has cryptography hiding in it. The microprocessors have firmware update elements in them, the microcode updates. So the drivers, applications, every device you carry has cryptography. How do you find it all? Well, if you go check out the NIST Cybersecurity Centers of Excellence, and even if I had this up on a slide, you'd never be able to read it. Just search for this if you want. There's an effort at NIST with industry to build tool chains to do this, to build tools that scan networks to find what cryptography you have, to scan source code to see whether you have cryptography in them, to scan configurations to see, did you bother to turn it on? That is where the action is at. So if you're a crypto person, I can geek out with you on the side. Quantum, all you need to know about quantum is, you got to fix this. And the solutions are coming. They'll be there. But the things we need to do, find all the crypto you have, figure out the plan for how you're going to replace it, and then start building the programs. So that's the real road ahead for quantum. It's the math's done, the technology we can have fun with. The road ahead's the grunt work, the hard work, whatever, of fixing the actual systems, finding them and fixing them. We know at a high level what to do. What everyone needs to do is go find their particular spots and start swapping stuff in. And with that, I think I actually have question time. So, although you either have to speak really loud and I repeat the question, or you have to go find the mic in the back. Or you're all tired of hearing from me and we can all call it good. Ooh. Okay. I wore everybody out. Oh, no, I see a couple of hands in the back, even near the microphone.
Can you hear me? Okay.
Yeah.
You hear me fine?
Yep.
Okay. So I just have a question. I know you addressed it a couple of times already, that quantum computing is kind of this all-encompassing thing that's hard to grasp at this point in time for a lot of us. Just as somebody in the cybersecurity field, really as I'm watching it, I'm trying to get to my question. As I'm watching it, I'm trying to see how can I prepare myself to be ready when quantum computing becomes something that's more widely used, in the government sector and also in the private sector. So I guess my question to you is, how can general cybersecurity professionals begin to maybe understand more about quantum computing and prepare themselves for when it becomes, what it will be one day? That makes sense.
Yeah, no, that makes sense. It's an interesting question. So let me nuance this a few things, right? So there's quantum computing is a threat to cybersecurity. And all you have to do for that, literally, is swap the algorithms, which is a huge job. Now, quantum computing, the other side, which I did not talk much about, is, okay, now that I've solved the problem, and as a cybersecurity professional, quantum computing is no longer my problem. Quantum computers don't affect me. Now what? That is a really cool science question. And there are a lot of people working out what are quantum computers good for other than ruining cryptographers' lives, or maybe getting lots of funding. I'm not sure which. And the answer is actually a little unclear. So there's a whole bunch of DARPA papers that just came out, right? So quantum computers, in theory, are a great way to solve certain chemistry problems, certain maybe machine learning problems, maybe some data search stuff, maybe some development. But we're kind of in that stage right now where people are just figuring that out. So strangely, unless you really want to be on that cutting edge, that's one that I'd watch from a distance and just go, okay, cool. Maybe somebody will come up with a way for quantum computers to do, malware discovery or behavioral stuff. But there's still kind of the level of, okay, where is this really going to have a payoff? Because there have been a few cases where everyone goes, quantum computers will solve this problem, then someone comes along and goes, machine learning solved it, woohoo, or, something else, we don't need that anymore. So there's a lot of work going on figuring out what else quantum computing might work in other than this, but it's kind of early days.
Okay. Well, thank you very much.
Yeah. Okay. Yep.
Hi. Well, let me first start by saying that I work for a QKD vendor.
Uh-huh.
So I'm on the other side of this discussion. But I wanted your take on how opposite do you think QKD and PQC are, and can they be combined in the future for a complete secure QKD? Anti-quantum computer solution.
So all right. So QKD combined. So all right. I can go several different ways with this. One is, right. I in principle, I should always say layering is good. Layering is good. Layering is sometimes not good. It's complicated. CSFC is one of my opposites. We tie in with layers and layering stuff, and there's always back and forth about, do I mix things? There are ways you can do different sorts of programming and merge. The QKD is an interesting one because, there are some spots where I think QKD could be useful. I think especially the technology going in as we start trying to exchange quantum information is going to be where it ends up. I can't predict when that happens. Right? I'm not going to write a standard for how to secure comms between quantum computers until someone shows up with a quantum computer and I know exactly how it works and what they want to secure. But I know when that happens, I'm going to have to exchange quantum information, which is basically what QKD does. It exchanges entanglement between different spots. One notch up, right? QKD is kind of like the first step of, I got to get entanglement and then run some things. I'm not quite sure where it's going to end up in the medium term. Now, I have to be careful, right? I work in national security spaces. We're very paranoid and very conservative. And the other thing I should say about QKD is it's physics-based. And so that means you have to build hardware that has very specific properties. I know how to do reliability work on a digital computer. And I've got decades of experience and standards on that and how to deploy that to national security systems. When I go into physics, figuring out how to make things reliable and meet all the other properties, it takes us many years to figure that out. So when I say, we're not doing QKD like in the next little while, it's because there's a lot of thought that we have to put in. We're slow on everything. That's a big enough change. And in a lot of our first use cases, a software fix gets us what we need. That's not saying, QKD is never going to go anywhere. It's just, in the space that they operate, it doesn't fit right now neatly. But we'll see where things end up, right? I know it's being deployed in places, and
that makes sense. Thank you very much.
Mm-hmm. Yeah. Yep. All right. Anybody else? Otherwise, we got 2 minutes early. I don't think we're in trouble for ending early. So, all right. Well, thank you. Thanks for listening, and I'll be around for at least a little bit.